This one's really, I know that a lot of you guys were like, I get it when I see you do it. I can follow along and it makes total sense. But when I get home and I try to do it on my own, I'm screwed. And that's generally what happens. Okay? Now, one of the things that we go through when you're learning stuff is that it's okay to struggle. And that's part of learning. It's okay to not get something instantaneously. And it's okay that you have to try harder at something to do it. It's fine. And that's every once in a while you come across something that is out of your comfort zone. And there's nothing wrong with that because it helps you learn in the long run. One of the things that you look at here is that if you look at the two setups that you have, you've got tangents on the left, cotangents on the right. In my mind, I know that tangent and cotangents are inverse properties of one another. Okay? I know that somehow I can get away from writing a tangent and I can turn it into a cotangent. And if I look at it, notice how the signs, like the plus and minuses, don't change. Now, how can I rewrite tangent in terms of a cotangent? Right. So if I wrote it as 1 over cotangent minus 1 over 1 over 1 over cotangent plus 1 over 1, doesn't that force me to get a common denominator? Yeah. What's the common denominator between a cotangent and a 1? Cotangent. Fraction on the left has a cotangent. Fraction on the right needs a. And it's the same thing in the denominator. What do you do when you have fraction divided by fraction? Come up and you multiply by the reciprocal. So then this becomes times cotangent plus u. And there you go. Of all of them, even for me, I did this problem 4 times before I figured it out. And it's one of those that you just, I'm sure you've heard this, the struggle is real. So the struggle was technically real on that one. And I'm not kidding. When I said that I tried this problem 4 times. I knew you were here. I thought you would have grabbed it. Whatever was that? This whole page is me trying to do number 11. And then I realized, oh, all I have to do is add. So it happens. It's okay. One of the main things about learning is really being out of your comfort zone because it forces you to figure out what was going on. What else do you want to look at here? 8. Right. Yes. It's nice when you have somebody at home that knows what you're doing, right? I will say that is a distinct advantage for some people. What else do you want to see on this one, guys? 8. Okay? Now, in this one, you're going from multiplication to subtraction. And a lot of times when that happens, that means you have to figure out some way to create a distribution. So if you have Michigan's that way. If you have multiplication to addition or multiplication to subtraction, that meant something had to be rewritten in terms of one of the identities. Because with the identities, you have additions and subtractions. For example, if I rewrite sine squared, I do tangent squared times quantity 1 minus cosine squared. Distribute. Tangent squared is 1 over what? Sine squared over? Okay. Again, it's the idea that you look at what you're starting with and then go, all right, how do I get that to look like what I need to end with? So when you start with the idea of multiplication and you end with something that has subtraction or addition, that meant that more often than not, one of the identities had to occur because you could rewrite some of these in terms of adding or subtracting. That's kind of the little hint as you get into those. And I know we've talked about a bunch of different little hints, and every problem's a little different. That's kind of the way I would go with that one. And then you guys said which number? Was it 8? I did 8. What was the other one you said? 12? Okay. 12 isn't as bad as it looks. Okay. Ladies and gentlemen. So 12 isn't as bad as it looks. Because what is 1 plus tangent squared? Secant squared. So what happens here is that you rewrite the denominator and then split it into 2 fractions. Is that what you did? Nice. So once you get a singular denominator, you can rewrite it as to 2 fractions and then mess with it. One minus secant squared is cosine squared. Then you get a complex fraction of sine squared over cosine squared divided by 1 over cosine squared, which then brings up that 1 over cosine squared and flips it. And you get that. And you wind up with cosine squared minus sine squared. Which means I just need to rewrite everything in terms of sines. So in order to get sines, I know that cosine squared is 1 minus sine squared. And that's how I get the 2 sine squared. This trick here is usually what you're going to see a lot of when we get to the equation stuff today. It's mainly that stuff. All right, it's mainly that. Lots of little ones like that. Okay. What else you got? Anything? 14? It is. The difference of squares twice. Oh, yeah. Think of it this way. Think of it like that. Is the first term a perfect square? Is the last term a perfect square? Is the one in the middle operation in the middle a subtraction sign? So then I get x squared minus y squared, x squared plus y squared. Now, with those properties, I have cosecant squared plus cotangent squared, cosecant squared minus cotangent squared. If you go and look at your Pythagoreans, the relationship between cotangent and cosecant is if I move the cotangent over, I'll get cosecant squared minus cotangent squared, which means that part, this part is equal to 1. So that's where you get that. Because it's 1. Yay! Okay. Now, is it wrong to assume that we're probably at about a 80%-ish? If you can honestly say that you're about 80%, 70, 80% on this, you're fine. Seriously. Because, like I keep saying, this stuff isn't the easiest in the world, and it's okay to struggle at it. Because you just keep working. You keep trying. If you get to a point where it doesn't work, you stop it. Don't erase it. Just start over. Okay? Like I was doing with my stuff. When I knew that I got to a point where it wasn't working, I didn't cross it all off and go back and erase it. I just wrote below it and started over. Because that way I knew to look where I made my mistake. I knew where to figure out where I went wrong. And then I would try something different. That's the idea with these things. And it's perfectly fine to struggle. It happens. Okay? So let's talk about equations then. How does this stuff relate to equations? Well, we've done this a little. I had that one problem before. We had some problems in the past. We had equations, and I said we didn't have to do this style. So today, we are. Was it less than? I was going to rewrote it. And we're going to solve this one on the interval of 0 to 2pi, which means we're going to list all possible solutions of the equation. Now, what we're going to wind up doing here a lot of times is that when we solve the equations, we're still going to get a side equal to 0 like we were doing before, because we had to factor stuff and do things like that to figure out how to undo sines, how to undo cosines, and look for things on the unit circle. But what we need to do is we have to be able to write our trig functions in terms of just one of the trig functions. I can't simultaneously solve for two of them. Not yet. There's formulas for it in pre-calc. You guys get a formula sheet. Don't worry about it. Okay. So first things first, if I'm going to set one side equal to 0, what am I going to move? Bring it over. I get 2 cosine squared minus 3 sine x. Bless you. And I have that. Okay with that? Now, this is where we have to make a decision on how to rewrite in terms of one trig function. The idea here a lot of times is to always rewrite the squared term in terms of the non-squared term, because the squared terms have Pythagorean identities to them. For example, sine squared plus cosine squared is 1, which means cosine squared can be rewritten as sine squared minus, or 1 minus sine squared. Let's move it over. Okay? So I get 2, 1 minus sine squared all I'm doing is I'm using the Pythagorean identity to move things around. Okay. Now what do you think you do? Exactly. So you distribute back in. You get 2 minus 2 sine squared x minus 3 sine x is 0. And now you're back to a plain old boring factoring. When you factored problems before, did you want to have first term positive or negative? Positive. So instead of, would everybody be okay by, in your minds, you know that you would just add everything to the right side? Or can I just change the signs of everything on the left? And signs, I mean S-I-G-N. Okay. So I'm going to put it in descending order and change my signs. So I'm going to get 2 sine squared plus 3 sine x minus 2 is 0. And now, if you, I know some of you guys still like using that u substitution. If you wanted to do that here to factor, go ahead. If you don't, it's not a big deal. Because all you have to ask yourself is what times what is negative 4 that adds together to get positive 3? 4 and negative 1. You look like I was crazy there. What times what's 2 times negative 3. All right. So I would write 2. I'm not going to use the u substitution because it's not a big deal. So I'm going to say it's 2 sine squared x minus 1 sine x plus 4 sine x minus 2 is 0. And what I'm generating here is a factor via grouping problem. Well, good morning. What's up? I've got stuff I got to do. I don't think I can. I don't know. Probably not, because I got to run off quizzes and stuff. So. Sorry. What do I do now? I GCF it. Yeah, you group. If I GCF that out, I pull out a sign, and I get 2 sine x minus 1. Out of here, take, oh, not negative 2, excuse me, take out a positive 2. I have that. Are the two things in parentheses the same? Yay! Just like before, that's kind of what you need to do. Hooray! Oops. So then I have 2 sine x minus 1 and 2 sine x, I'm sorry, sine x plus 2 is 0. And all I'm doing here, instead of rewriting what the two terms are, we know we have to set them equal to 0 to make it work. So when I do that, excuse me, one of those make no sense. So which one makes no sense? Which one, Matthew? The right one, as in the correct one, or the one on your right? The one on the right, correct. Yeah, because will I ever get a value of sine that's going to equal negative 2? No. So I know that this one will not work. That one won't work. But I go to the next one, and it says that, all right, what angle has a sine value of 1/2? Got to go back to your circle. Sine is opposite over hypotenuse, which means your opposite is 1, your hypotenuse is 2. That would be a 30-degree angle. You guys might want to revisit that. 30 degrees in terms of pi is pi over 6. Very good. So I am positive pi over 6. Where else is sine positive? First quadrant and second quadrant, because it's a y value. There's your answers. It's bringing back what we've done. And that's the thing. Some of these do take a little bit of time, but honestly, the complexity of it isn't crazy. It just takes a little bit of time to go through because this is very procedural. Do this, do this, do this, do this. Draw it. Okay. vaguely remember some of this, I hope. It was about a week or so ago. Well. You'll get over it. Same idea. Same basic principle here, ladies and gentlemen. I need to be able to rewrite something in terms of, so they have the same trig value. In this case, I have tangent squared and secant. Just so happens there's a Pythagorean identity with tangent squared and secant. I know, right? It's convenient. So how can I rewrite tangent squared? Careful. Secant squared minus 1. Okay, secant squared minus 1. So I get 2. I'm doing this one on the interval as well. I forgot to say that. I'm going to do this one on the interval. We'll worry about general solution stuff later. Is everybody okay that I skipped the distributive step, knowing that I was just going to put it in descending order? I just distributed the 2, and I knew it was going to have to go at the end anyway, so I just kind of skipped the step there. Okay. And it winds up being what times what's now -4, that adds to be -3. -4 and 1. You might realize after a little bit of time here that the factoring portion of this is not going to be crazy, because all of these problems kind of have to work, and if they work, they have to be special triangles. In order to be special triangles, they can only work with certain numbers. Go figure. Okay. Group it. Are they the same, Mackie? Yay! So I write them down. And what I'm going to do, like I've done in the past, I'm just going to go right ahead and set them equal to 0. Because we know it's going to have to get there anyway. Now, here's when you have to be careful. You guys got questions? I'll just give you the quiz. Seriously. Before you get too involved in this stuff, what you want to do is you move your stuff over. And trust me when I say this. Don't try to solve equations when they're reciprocal properties. Okay? You will screw something up. Okay? Trust me on this one. What I mean is this. Secant of x equals 2. I can figure out where my secant value is equal to 2, but it's a pain. What's the reciprocal of secant? What's the reciprocal of 2? Do it that way. What angle has a cosine of 1/2? What I'm looking at here is by doing it that way, it's an easier setup to draw. Okay? Your minds are more, I wouldn't say adapted, but your minds will be more apt to think of the special right triangles when they're in terms of the standard trig functions versus any of the reciprocal properties. Doesn't mean you can't do it. It means it's a good suggestion not to do it. So if I'm looking at this, this means what angle has a cosine of 1/2? Well, that means that my adjacent is 1, my hypotenuse is 2, and then my opposite would be √3, which makes this my 60. 60 degrees is what in terms of pi? Pi over 3. And where else is cosine positive? 4th. Very good. So pi over 3, and, well, this would be 6 pi over 3, so it would be, very good. All right, that gets me there. And I do the same thing with the other part. Subtract 1, divide by 2. I get secant. Flip everything, and it's asking you what angle has a cosine value of -2. Doesn't exist, right? And that's where some of you guys will mess up. Oh, it's got to be 1/2, or it's got to be 2. Nope. Cosine and sine values are always inclusive between 0 and 1. Or -1 and 1, sorry. What happens though, or what do you think you should do? What happens when you don't have a Pythagorean identity? Think of it this way. Think of it this way. What would you do if it was this? What was it? Multiply everything by x. If you multiply everything by x, do you keep everything? Does it stay balanced? So you do that, right? So what would you do here? Exactly. The idea of how you undo stuff to manipulate algebraically doesn't change at all. When you have reciprocal properties, sine and cosine, you can do this exact style thing. Here's what happens. When you do it that way, you have 2 sine x plus 1 over sine. And think of it as you want to get rid of the fraction. How do you get rid of a fraction? Well, you multiply everything by the denominator, just like you have in the past. That process of algebra hasn't changed. It just so happens that there's more letters to it. So if you multiply everything by sine, you get 2 sine squared plus 1 is 3 sine x. And now you're back to a problem that's relatively simple. Right. What do you do first? Bring the 3 over. What times what's 2? You add together to get -3. And 2 -1. And then you group, just like we've been doing over and over and over again. I really wanted to make sure I showed you guys this example because there's a part here that you're going to screw up. So you have 2 sine x minus 1 is 0. sine x minus 1 is 0. One of them was pretty quick. You get what angle has a sine of 1/2? We've done this one already. Sine of 1/2 is where? I/6 and now the other one's asking where is sine equal to 1? Bring that back. Bless you. Sine, x or y value? It's y value. Where is y equal to 1? Pi/2. It wouldn't be 3 pi/2 because it's not plus minus. Oh, good times. All right, last one. You guys do this one. Bless you. Now, this one, you'll have to do two things. You'll have to utilize two things here to make it work. Again, solve it on a 1 revolution. See how you do. What does that get you? It doesn't get you anywhere. Obviously, did you recognize that cosine times tangent equals sine? That's the trick. What happens here is that sometimes they'll embed a quick simplify prior to being able to do a Pythagorean switch. And this is a prime example of that. So what happens here is that you get cosine times sine over cosine. That simplifies first. And then you're left with sine x minus 2 cosine squared. And now you would rewrite cosine squared in terms of sines by saying it's 1 minus sine squared. Now here's where you're going to screw up. What happens here is that you'll forget that the -2 is out in front, and you want to distribute that to the second part. Happens all the time. This negative to negative is one of the things that I've seen throughout the entire school year that you guys tend to miss, I should say. And all I did is I just brought the 1 over. To put it in descending order, we'll get 2 sine squared plus a sine x minus a 1. And now you're at a factoring thing that we've seen. What times what's -2? You add together to get 1. 2 again. So. What's that, sir? No, what you got? What was it? I'll tell you. Fine. The stairs were there when GCF. Hey, look at that. It winds up being like the same answers again. So you get sine of x plus 1 and 2 sine x minus 1. So it's asking you what angle has a sine. What angle has a sine of -1? And what angle has a sine of 1/2? Now where's sine -1? 3 pi over 2, 1/2, pi over 6, pi over 6. Today we are only going to focus on integrals. We'll not worry about general solutions. We will revisit general solution setups mañana. I just don't want to kick in stuff. Go. Yeah, you'll just do that one, the left-hand column. So, it's between 0. I apologize. It should just say less than 2 pi, not less than or equal to 2 pi. I just realized I wrote that. So, just do those 6 in terms of one revolution of listing problem, of listing out. Tomorrow we will revisit how do you set up general solution. We'll do that. We'll start that with non-trig identity style problems to remind ourselves how to do that, and then we'll jump into using trig identities. So if it struggles a little today, that just means tomorrow's easier. Just like on Tuesday, you guys struggled mightily. What happened Wednesday? It was a bit easier. And that's the thing. That's how we learn. It's how we overcome. It's how we do stuff. It's how we math. Oh, I would suggest that you write down the 3 trig identities on that page, because I bet you might have to use it once or twice. Maybe 6 times.